Welcome to the 13th lecture for Physics 4B. We wrap up our discussion of electrostatics in this lecture by demonstrating a couple last properties of conductors in electrostatics and introducing a device you will see many times in the remainder of this class, a parallel plate capacitor. In the first lecture segment, we look at the conductor properties 3 and 4. The knowledge of which is useful in solving certain electrostatics problems, and also in working with the high voltage setups sometimes. And after a brief discussion on dealing with the units in electricity, and also magnetism, we introduce and analyze a setup that we will refer to as a parallel plate capacitor. This setup gives us a particularly simple relationship between the electric fields and the voltages, and its simplicity also serves as a useful background as we develop concepts in electrostatics and later magnetism. As an illustration of its usefulness, we will use this setup to discuss two things. One, different energy formulas in electrostatics, and two, dielectrics, and their effect in an electrostatic setup. We will set aside a lecture for a review of electrostatics and an in-depth analysis of a dipole setup, and then we will move on to electric circuits and magnetism.
So this is the starting place for us here. And the thing I would like to drive, or the situation I would like to investigate, is let's say we have two conductors, one of one radius, R2, one of another radius, R1, where R2 is greater than R1. We connect these two electrically. This is a conducting wire. So that all the conditions I was putting here is satisfied, that this entire thing can be considered as one conductor. And really what we are doing this as an example of is imagine a weirdly shaped conductor, like if this conductor, then it has a part with a different curvature. It has this part with a relatively large radius of curvature. It has this part of T, where the radius of curvature is small. And dealing with this arbitrary shape, that is difficult. We are not doing that. So what we are doing is using this as a model that is simple enough to analyze, so that we can get some general rule of thumb that's applicable in a wide variety of situations without being quantitatively too exact. So I want to analyze this setup, and as we are analyzing it, what we are ultimately interested in are the properties of electric fields in this setup. So what do electric fields look like in this setup? And I want to point out some pitfalls that I want you to avoid, or I want you to recognize and not fall into the pit. So here are some naive thinking analysis that may allow you to draw mistaken conclusions, which actually in this context might be right, but you arrive at it in a mistaken way, so it's still wrong. Which is not also one very easy mistake to make is the naive application of Coulomb's law. You have this formula memorized. Electric field of a point or even a sphere is equal to Coulomb constant times charge over r squared. So this is the naive mistake you can fall into. You look at these radii and you think, yeah, the electric field goes as 1 over r squared. So of course, when the r is smaller, then electric field is stronger. So you conclude that when you look at electric field here, for example, and you look at electric field here, for example, and you conclude, yes, of course, E1 is greater than E2. Now, this inequality itself is not wrong, but the reasoning process that went into it is wrong. because for that reasoning process to be valid, what had to be true is that the amount of charge on both of these spheres had to be the same, and they are not. They are not the same. And nothing in the setup actually forces them to be the same. So it shouldn't surprise you that the amount of charge that's on this smaller sphere is not the same amount of charge as on this larger sphere. Then you might now go the other way too much, where you say, oh, so this larger sphere, it probably has more charge. So because it has more charge, the electric field here is going to be greater. Maybe it could be. It turns out not to be. So what we instead have to do here is, instead of being sidetracked by all the things we don't know, and frankly misapplying this formula, let me erase it, rely on the things that you do know. And the thing that you do know is, oh, this is such a misleading label. The thing that you do know is the conductor property number 3. This is not the conductor property number 4. This is the conductor property number 3. So that is a property that you know, which means you can say this.
So this is a rule that you can infer from the rules we have covered so far. But it'll take more than a few seconds that we have for you to guess that. So let me give you that rule. So far this is what you know, right? Electric field is 0 inside a conductor. So let me have you imagine a path that goes from this point, which is at V0, and follow the path inside this wire and end up at this point here. What is my change in voltage along that path? Does my voltage change along that path? Yeah. If we are having hard time seeing that voltage doesn't change, come back to this definition. Voltage change is electric field times the displacement. If your electric field is 0, that's one of the rules, then voltage doesn't change. So that's the third and the last rule about conductors, which is that voltage is constant inside the conductor. Or, delta V is equal to 0 inside the conductor. Now, I want you to be careful. This does not mean voltage is equal to 0. On this conductor, voltage is not equal to 0. It does not mean voltage equal to 0. It means change of voltage is equal to 0. Because of this, the surface of a conductor automatically defines an equipotential surface. This, by definition, is an equipotential surface. Because inside the conductor, it's all same voltage. So when you look at just the surface, it's all at the same voltage. So, yeah.
So that is a property that you know, which means you can say this. If the surface of this conductor is at some voltage V0, you can say the surface of this conductor here is also at the voltage V0. That is the quantity that is being held constant. And this is a feature that feature in physics problem solving and possibly other quantitative problem solving that you're going to see over and over, which is you have some relationship which relates multiple quantities and usually 3 or more dynamical quantities. And you have to know something additional about the setup beyond that relationship to fix one of those 3 quantities so that you can talk about how the remaining 2 are related to each other. And this is exactly a setup like that, because with that electric field, radius, and charge, that formula for the electric field of sphere, you had the 3 dynamical quantities. So you needed a way to fix one of them. Now it turns out with that particular relationship, you don't have a way to fix any of them. So give up on that. What you can instead use here is this conductor property number 3. And I will demonstrate how we can use this to conclude correctly that the electric field right outside this sphere is greater than the electric field right outside this sphere. So Let me move the question over so that I have some space to write stuff. This is the electric field of a sphere, spherical charge distribution. It can be actually any spherically symmetric charge distribution. For the simplicity's sake, I can say it's the spherical shell, electric field of a spherical shell. The magnitude of that electric field is given by Coulomb constant times the charge on the spherical shell divided by the distance squared. That's the Coulomb's law, and we talked about how using Gauss's law we can derive that. Now, using this expression and using the definition of a voltage, which maybe I should have written it down here. Definition of voltage, change in voltage is equal to minus the electric field times the dot product of electric field and displacement. This should remind you of the work done by conservative force. So using the definition of voltage, we can derive an expression for voltage of a spherical shell. So voltage of a spherical shell is given by this. And this is under a very specific convention, which I'll write down right after I write down the formula. The formula for this is the Coulomb constant times the charge divided by R. And there's slight distinction between the two, whereas the electric field is a vector quantity, voltage or electric potential is a scalar quantity. It's like energy, it doesn't have direction. And this particular expression, it depends on this convention, which is that voltage as a function of R goes to 0 as the R goes to infinity. So okay, I think now I have everything here. So this is the set of expressions I can write down. Let me try to organize my expressions in terms of ones that relate to the larger sphere, so the R1 sphere, and the expressions that relate to the smaller sphere, R2 sphere. So I can talk about the voltage on the sphere, voltage on surface. Both have a voltage of V0, that is what we are keeping constant. And I can rewrite each of these expressions using this formula here. So I don't actually know how much charge is on each of those spheres. So I'll leave that as a variable and write this down. On the R1 sphere, let's say there's a charge Q1 at a distance of R1. And this expression is equal to V0. And for our R2, that's the voltage, and this formula still remains valid. I just had to be sure to use Q2 and R2. Coulomb constant times Q2 over R2. So this is the expression for voltage at the surface of this conducting sphere. And because of the conductor property number 3, these two things happen to be equal to each other. Okay, let me just close that off there. And let's try looking at the electric field on surface. You have to be careful here. It's the electric field just outside the conductor, not inside or whatever. Then here, I don't know the value of the electric field. So I would like to start out with the formula. So starting with the formula, it's gonna be the Coulomb constant times the amount of charge, Q1, divided by R1 squared. And I'll leave that as just the magnitude. I'm not gonna worry about the vector portion. And I can write down the same expression for R2, Coulomb constant times Q2 divided by R2 squared. Now, I hope you begin to see some very useful substitutions that can be made that simplifies on the algebra and frankly saves time. So let me make that obvious. I'm going to factor out one factor of 1 over R1 there. 1 over R1 and So to factor that out, I get rid of one factor there. And same thing here, factor out 1 over R2, erase that there. So this combination of expressions here, that is this. This combination of expressions here, that is this. So I can make the substitution and end up with the expression for the electric field outside this rounder sphere, and I get V naught over R1. Over here, I get V naught, same V naught, over R2. So these are the expressions for the electric field that outside here E1. This is the expression for electric field E2 outside the smaller sphere. And it's on this basis you can say E2 is greater than E1. And note how the factor by which E2 is greater is smaller than it would have been otherwise. Under the first naive analysis, you would have said, let's say if the ratio of the radii are factor of 2, if this radius is half as large as this one, you would have said, oh, electric field, they are different by a factor of 4. But that would be wrong. The relationship is linear because the amount of charge on these spheres are different. There is a smaller amount of charge here, but it's not such a smaller amount that it causes electric field to be smaller than it is here. So that's the conductor property number 4. Let me write that out explicitly, which is erasing this conductor property number 3. Conductor property number 4. So this can only really be stated in a qualitative way because this particular example is a deliberately simple example where we could analyze it in detail. So conductor property number 4, the way we qualitatively state it is electric field outside charged conductor. And I probably should qualify it as in an electrostatic equilibrium, although I think a good chunk of this holds true when it's not equilibrium. So inside a charged conductor in an electrostatic equilibrium is greatest, or is greatest or greater. Let me say is greater around sharper corners. Or if you think that's a little bit too, I don't know, terribly informal, because what I mean by sharper corners, it's not very rigorous way to state it. It's not very mathematical. You could say instead of sharper corners, that's one way to say it. Around the other way would be around the surfaces with smaller radius of curvature, which is the mathematically precise way to say sharper corners. Any kind of continuous surface, you can imagine fitting a sphere to it, and the sphere that will be tangent there. And I guess tangent is where the derivative is the same, and where the second derivative is the same, that's where you have the same radius of curvature. So you can associate that measure with electric field strength. And because for arbitrary conductor shapes, it depends on the exact shape. We don't have a formula for it, but we can say that when I have a conductor that looks like this, electric field is going to be strongest here. And that's why with the electric whirl demo, you see it spinning the way it spins, because where the ionization has to happen is at the tip of those arms where it's been deliberately sharpened. So that's conductor property 4. Yeah, I mean, it doesn't work quite as well, but you can still see that it works. Let me just stop it and spin it the other way. And I think if I turn this, then it'll eventually stop and start turning the other way. Anyway, it'll work a little bit more easily if I bring the wire closer. So let me wire a bit closer. Still not touching. Let's see how well this works. So it's a fun demo. Now this is the kind of demo where I can't do anything quantitative with it because the kind of measurements you might be able to make, I think they would be fairly, there'll be too many things that you don't know or that it can't be measured well. Let me talk about units a little bit now so that I can at least say that we have gone over it. The truth is the units in electricity and magnetism can get very, what's the right word? Convoluted or complicated. So units in electricity and magnetism can be very complicated. So I want to take a little bit of time to make sure I give you some guidelines for approaching units. So my guideline for approaching units is to really remember the equations. And once you remember the equations, you will realize that equations tell you what the units are. So for example, let's say you want to know the unit of electric field. Can someone here actually tell me what units electric fields are given? Gauss is a unit of magnetic field. Yeah, also not an SI unit. SI unit is Tesla. Like 10,000 Gauss is 1 Tesla. But anybody here know unit of electric field? It's understandable that no one knows. For one, we didn't cover it in class. Two, there isn't a name for that unit of electric field. It's like, I don't know, with the momentum, we didn't have a special name for the unit of momentum, right? Even though momentum is a super important quantity in physics 4A. It's the same deal with the electric field. It's a very important quantity in electrostatics, but there's no unit that's just for electric field. So what you have to do is, there are two equations that involve electric field. It's this equation here, the one that relates electric field to force, and the other equation is this one here. But let me also highlight this one, because these three equations, more than anything else, will give you a guide into the web of relationships between electrostatic units. So let me start out with this one. This is the easiest one. So we have force is equal to charge times electric field, right? So that tells you the relationship between the units that you already know. What unit is force given in? Of course. Yeah, newtons, right? Everyone knows that. What unit is charge given in SI units? People remember the name? Yes. Coulomb, yeah. Named after the guy who discovered the Coulomb's law. So charge is given in coulombs. So this tells me what unit electric field must be in. It must be in the units of Newton per coulomb. Right? And this is one of the commonly used unit of electric field. Oh, there it is. That's it. So that's one unit of electric field. But actually, I guess if you are doing any sort of experiment with electricity, you'll find that most commonly used unit of electric field is actually not Newton per coulomb, but something called a volt per meter. That's because it's coming from this relationship here. So let me actually do the other one first. I don't think I ever properly introduced the unit of volts. So volts are the unit of electric potential or voltage. It comes from here. So when you look at volts is equal to some 1 over charge times some amount of potential energy. Then this is the new quantity that you may not know the unit of quite yet. But you know the unit for the charge and the potential energy. What unit is, what's the unit of potential energy? Crystal, what's the unit of potential energy? It's been a, wait,
been that long since we talked about energy, right? We did it in thermodynamics. It's the name of a guy. No. Joules. Do people really forget joules? Let me spell it out. The unit of energy is joules. This is the SI unit of energy. And to tell you the truth, there are many units of energy. Calories, well, I guess calorie is the only known SI unit I can remember now. But joule is the SI unit of energy. It's really important one. You should have it memorized, like for the rest of your life. So that's the unit of energy. 1 over charge, well, we did that already. So that's 1 over coulomb. 1 over coulomb. So unit of voltage. This is the left-hand side, which if we are trying to say it in terms of other units, you would say volts. Voltages are in joules per coulomb. But with the voltage, with the electric potential, it turns out that we gave a special name to this particular combination of units. We call this 1 volt, named after, I think his name was Volta, or was it Volta? No, that doesn't sound right. There's a guy who invented the battery. So this unit is named after the guy who invented the battery. Yeah, Volta sounds wrong for some reason. So this is the unit of electric potential, and it's a joules per coulomb. There it is. Now, the last unit relationship between units that's common, so it's good for you to know, is the relationship between the unit of electric potential to the unit of electric field. So that is based on this relationship here. Change in voltage is equal to, I'm just going to forget the minus sign, electric field times absolute value times change in distance, right? So the left-hand side, we are going to stick to the unit of volts. That's the named unit for voltage in electrostatics. So I'll just write down, left-hand side is in volts. On the right-hand side, what's the unit of length? Meter, right? That's the SI unit of length, meter. So the electric field, to make the units come out right here, it must have unit of volts per meter. So this is the sort of the place where electric field is. It just doesn't have a unit that's assigned to it. There's no name for the unit of electric field. So depending on who's making the reference, either people will use this. You see this a lot in textbook questions. But if you're actually doing any kind of real work with electricity, most people will use this unit, volts per meter. So I think we should go through one last exercise just to make sure we are on the good ground. Question?
Those aren't the same quantity.
Yeah, so I want to make sure that they are the same quantity.
Okay.
That's the exercise I want you to go through. Thank you for asking. Yeah, so I want to make sure, I mean, they are both describing electric field. So they better agree with each other. If they don't, we are in trouble. So let's just make sure that it is the case. So what I want to make sure is that 1 Newton per coulomb is equal to 1 volt per meter. Like, is that actually the case? Well, let's just write out everything and see. Whenever you're trying to see if the units agree, you just write it out in the basic units. Basic SI units are kilograms, meters, seconds, and now coulombs. So write out all this in terms of those. Let's see what we get. So Newton, I know how to write that, so let me do that. So the left-hand side is 1 Newton is kilogram times, let's see, mass times acceleration. So meter per second squared. Yep. All of that divided by coulomb. That's the left-hand side. Right-hand side, I have to write out volts. That's going to be in joules per coulomb. So joules is Newton times a meter. Everyone remembers that? Yes? Can I tell you how I remember how joule relates to Newton and other things? This is the relationship I remember. Work is force times distance. and work is energy, and this is Newton, this is meters. So, actually the advice I was giving at the very beginning, it applies to everything in physics. I don't actually try to remember the unit relationships. I try to remember defining equations, because defining equations will tell you automatically how the units are related. Okay, so volt, let me, do I want to do it? Let me do it in 2 steps. Let me first write down 1 volt per meter here first. So that's 1 joule per coulomb meter. Now let me write out joule. So joule is 1 Newton times meter per coulomb times meter. Oh, I guess I didn't have to go through all of this. Let me write it out anyway. So what a joule is kilogram times another factor of meter, so meter squared per second squared. That's a joule. For volts, I need to divide by coulomb. So divided by coulomb times, on the denominator, I still have meter there. So when you write it all out, then it's simple to see that once the meters cancel out, then this is equal to that. And the whole reason the SI unit system is set up is that once you work out the unit portion of it, then the numerical portion of it is super simple. 1 is equal to 1. You don't have to do any weird conversions like 3 feet to a yard or 12 inches to a yard. Or no, sorry, 12 inches to a foot. So you don't have to do that. So yeah, those are the electrostatic units that you should have seen so far. And now that we are talking about this setup, and we are talking about how to get electric field from voltage, now is the time for you to see all those relationships between units. So when I get electric field, I can describe it in terms of volts per some unit of length. And I'll tell you one of the popular unit for electrostatics when you're doing experiments, it's actually this. Kilovolts per centimeter is the one that I usually remember important numbers in. Like the dielectric breakdown strength of air is 30 kilovolts per centimeter. That's how I have it memorized. I don't have it memorized as whatever 3 million number you saw in the other thing. Good. Then let me move on by describing the system that forms what we are going to refer to as capacitor. It's actually a setup you have seen before. Let's use this as an example example of working out electrostatics for a particular situation. So imagine this setup. You have a parallel plate capacitor. So imagine this plausible physical setup. I have 2 conducting plates of some large area. So I have a conducting plate. The exact shape doesn't matter, but if you want to imagine a particular geometry, imagine it's a rectangular plate of some area A. One, and there's one more here. I don't think I'm drawing this all that well. Well, this is the front. Wait, which end do I want to be front? Let me not do the perspective. I'm just going to draw the side view. Side view is a lot easier. So this is the side view of the parallel conducting plate. So here's the plate 1. So this plate is conducting and area A. And I have another plate that's also conducting, also with the area A. So this applies to both plates. And with this conducting plate, this is what I'm going to do. So they are separated by some distance d. And I make sure that they don't touch each other, because if they touch, it'll be problematic for what I'm going to do now. And what I'm going to do is I'm going to connect both of them to a battery, to a voltage source that's going to provide some amount of voltage difference. So this end is connected through a conducting wire. This end is also connected through a conducting wire. to a battery. Let me draw it like a car battery or something. Actually, I realized I don't know how to draw a car battery. Negative plus. I don't know what it actually looks like. But it's a voltage source providing some voltage V naught. And for convenience's sake, we can say that this negative terminal here, this is at 0 volts. And this positive terminal, this is at voltage of V naught. Yeah. So you are visualizing this kind of setup where I have two conducting plates, one connected with a wire to some one end of battery. So this is at 0 volts. The other end is connected through wire to the other end of the battery. This is at voltage V naught. And I just want to confirm. So when I say the plate is at 0 volts, do I have to, what feature here can I point to say that the entire plate is at exactly 0 volt? It's not just at this point where it's connected. It's throughout the entire plate, I can say it's at 0 volt. Like so a part of this description here allows you to say that once I connected this with the battery, once I connect a single point with the wire to the battery, then I can say that this entire plane, from one end to the other, is at 0 volt. What allows me to say that? That it's a conducting plate. So this is one of the properties of conductor that we brought up last Monday, because it's an important property. So at electrostatic equilibrium, electric field inside the conductor is 0. That means once you say voltage of one point, then you know the voltage of every other point on the connected conductor. That's also the other reason why it's so important for me to stress that this other plate is not touching it. Because the moment this touches, they both have to be 0 volt. But I want to put this other plate at a different voltage. So it's connected only through this battery, which is providing the voltage difference. Good. Okay, so this is the setup. And does this feel like a complete description of setup? Like if I asked you to build this and gave you conducting plates and batteries, you can set this up, yeah? Yeah, so this is what will serve as our static electricity example. And there are a number of questions we can ask about this setup that's all already determined. So let me just write down a few of them that we can answer based on what we know about static electricity. So I'd like to ask, I guess, two things. That's some basic dynamic quantity that's useful to know. First is, well, I want to know what is the electric field around the setup, as in electric in between and electric field outside. Let me call them regions 1, 2, and 3. I'd like to know something about electric field in regions 1, 2, and 3. And once I apply voltage, I'm sort of going to assume that there must be charges around here somewhere that's associated with these voltages. So I'd like to know the charges. So how much charge on both plates, I mean on the negative plate and on the positive plate. Okay. So these two are basic electrostatic questions that I can ask. And if this is a complete description of the setup, there must be some way of getting from information that's provided here to the electric field. Okay, so this is a sort of a review / example. Based on what we have covered about electrostatics so far, you should have enough information to answer here. So how would we get to electric field? Chris? Oh, I thought you had. Okay, while you guys are thinking, let me write down some of the information as the things that you should have, you should know, should sound familiar, and I would really recommend that you have memorized by the time you get to exam 2. Let me start writing them down here. While I do that, a couple minutes, think about how you would look for electric field using the information that's provided there. But while you are thinking about that, let me just write down the information here so that in case you don't have them memorized yet, you have a chance to see it. Let's see. I'm only going to write down information in shorthand. I'm not going to explain a bunch of stuff because it should be familiar to you. All right, I think that's it. In terms of definitions and formulas that you are supposed to know, I think that's a comprehensive list. Right? It's not a long list, but for you to be able to say you understand what these are, that does take, that's what we covered for like 3-4 weeks. So this is a reminder to what we have been covering those 3-4 weeks. And, based on these, how would you say we should look for electric field here? Like what information given here could you use? Yeah, voltage is the quickest way to get to it. So, Kate is looking at this definition of voltage. And one of the key information that's given here is the voltage difference from this point to this point. And we should be able to relate it to the electric field, and some geometric information here. Yeah, so this, once you realize how to approach this question, this is actually a really simple question, right? Yeah, so let me just imagine a path somewhere in the middle so that I don't have to worry about any complications. So going from this point to this point here, my change in voltage here is V naught. It's increasing by V naught. So for part A, what I would say is label these points A and B. So change in voltage going from A to B, which is equal to V naught, is going to be, I always forget this, sorry, there's a minus sign here. So that's equal to, if I write down the full expression, it will be integral from A to B minus E dot dx. But it can be actually a lot simpler than that. Like in this situation, can someone tell me how this simplifies? Like I don't actually have to do the integral. I'm not going to do any actual integral. What allows me to avoid doing this integral altogether? The formula is derived from Gauss's law, but
Symmetry of the plane.
So symmetry of the plane. So what Kevin is looking at is this. In this setup, it would be really nice if we could treat this as an infinitely large planar charges. If it was, then we could use this formula here, right? Which says the electric field for a plane is really simple. It's a constant. There's no distance dependence at all. So yeah, I'm going to use that. I'm going to say, based on my familiarity with electric field of a plane, I'm going to say, so in the problem statement, I didn't say it quite yet, but I will say, in the limit where this area, or rather square root of area, is much, much larger than the distance d, we can treat this, approximate this, like they are infinite planes. And we are going to say our electric field will be like electric field due to an infinite plane, which is constant as a function of distance. So I can say, as I imagine doing this integral, I don't have to do the actual integral. I can just pull the electric field out, and this will be just minus the constant electric field times delta x going from A to B. Good. All right. So the left-hand side, the change in voltage, as I said, that's a V naught. That's a positive value. So let's say, so this is this arrow that's already drawn here. This is my delta x going from A to B. What direction is the electric field? Based on what you see here so far, would you say electric field points to right or points to left? Points to left, right? I have to do this dot product, multiply it by negative to get a positive answer. So that means the dot product should be negative. So as you're answering this question part A, you fill in some of the information that you weren't given to start out with. But this is the information that you have to start filling in if you are understanding the setup, and you can answer part B later. So there's going to be electric field pointing this way. So this is my sort of electric field line, more or less. So my delta V naught, or my V naught is equal to, so let me use this symbol here. The magnitude of this electric field, let me call that E naught. Then V naught is going to be equal to the magnitude of electric field, E naught, times the separation D. Here I'm dropping the signs because I just want to know the magnitude of electric field. But this is a correct expression. So you get this is really simple expression in the end. E naught is equal to the voltage difference divided by distance. Good. It's a really simple answer. And now what I don't want you to do is memorize this as a formula, because this is a sort of designed scenario where this will be true. But if I change one little thing, make this a cylinder, for example, then this won't work anymore. This simplifying step that we did depends on that this is a planar situation. Yeah.
So are we saying that the electric field is like the same strength along all of these?
Yeah. So at all these different points in the space here, the electric field is uniform. No matter how close you are to the plate, whether you are in the middle or how close you are to the other plate, they are all at the same strength. That's the result you get if the planes were actually infinite. Now, they are not actually infinite, but we are saying we are going to approximate it as being infinite. Yeah. Okay, let's move on to the second question. How much charge are on these plates? Let's figure out one thing first. What kind of charge is on what? Like, I have some sense that one plate will have negative charge, the other plate will have positive charge. Which way? Is the positive charge here or here? Positive charge on the high voltage? Yeah. Yeah. So you can gain confidence for that, especially after you figure out the direction of electric field. Because electric field should always come from positive charges. So if you have positive charge here, that matches with the direction of electric field you already figured out. So positive charges here. And if you have negative charges on this side, electric field should go towards the negative charges. So that matches with your understanding of electric field already. Okay. So looking at this, that actually gives you maybe one more rule that you could remember. You don't have to. So higher voltage, more positive voltage, is around the positive charges. Lower voltage or negative voltage is around the negative charges. And hopefully all of this makes intuitive sense, especially considering this relationship here, that voltage relates to the potential energy. So, and the way to use this intuitively is to imagine how a positive charge would act in a particular electric potential. So, in this setup, if I place a positive charge near the high voltage, do you expect it to get attracted to the high voltage or get pushed away from high voltage? Pushed away based on the direction of electric field, right? Now, you can consider energy. So I have some charge at some place of some potential energy. When I let go, naturally, do you expect it to go lower potential energy or higher potential energy? Lower, right? If you allow it to move, all things tend to move towards the lower potential energy. And this is what this charge does too. So if it's a positive charge, when you place it near the high electric potential, high voltage, then it has a high electric potential energy. So when you let go, it's supposed to move towards the lower potential energy. And for a positive charge, that means going from higher electric potential or voltage to the lower electric potential or voltage. Okay? There's a reason I keep saying voltage and electric potential together. Imagine this was, I don't have anything to represent. Okay, let's say this is negative. Imagine this was a negative charge instead. On which end does it have higher potential energy? Does it have higher potential energy here or here? Near the negative charges, right? There are different ways to see it. So the place where it has more energy is place where it'll get pushed away from. If this is negative, then it'll get pushed away from other negative charges. Another way to see it is through this expression here. So potential energy is, move this around, charge times voltage. So when the charge is negative, that means higher electric potential or voltage corresponds to actually lower electric potential energy. Okay? So if this is a negative charge, then it still has higher electric potential here. But if it's negative charge, then higher electric potential actually means lower potential energy. Get all of that makes sense? Kinda? Yeah. Okay. Okay. Yeah, it's not a difficult thing, but once, yeah. Okay. So we are trying to figure out, okay, so we know what kind of charges where positive charges here, negative charges here, and what we want to answer is, well, so how much charge is here? What's the actual magnitude? What's the amount of positive charge here? And what's the amount of negative charge here? Oh, I realized I skipped a question. For the electric field around, I answered one question. This question for the electric field here, right? So that's for region 2. I never got to regions 1 and 3. Can people tell me what electric field is here and here? Yeah, 0 here and 0 here. Katie, can you tell the class how you got that? Like, yeah, some of different contributions. So what the thinking process that Katie is going through is remembering the superposition principle. So let me sketch this up because this is useful for what I'm going to do next. So imagine you have this electric field due to a single negative plate. Let me draw that as one picture. And electric field due to a single positive plate. All right? Then here, the electric fields look like this. It points towards the negative plate. Towards the negative plate. And here, electric fields point away from the plate. Point away from the plate. So you can see that in the region that we are labeling as region 2, this region here, region 2, you can see that the contribution to the net electric field from each one of these charge distributions, they add. So that you get this non-zero electric field. But outside here in region 1 or here in region 3, you see that their relative directions are opposite. So Kate, can you say, how do you know they cancel exactly? They are at different distances, right? So how do you know that they cancel exactly? Same, so how do you know they are same magnitude? Because you are remembering that it's an electric field of a plane which does not depend on distance. So here, the contribution to the net electric field due to the single plate on either side, the magnitude is electric field here is equal to surface charge density over 2 epsilon naught. Same thing here. The magnitude here is equal to surface charge density over 2 epsilon naught. So what you get is in between where they add, the total electric field, the result of these two being added together, is equal to sigma over 2 epsilon naught times 2, or add them together. So you get sigma over epsilon naught. This is the expression for the electric field between the two plates due to the surface charge density of plus sigma and minus sigma on those two sides. And outside here and here, they cancel each other out and they go to 0. Yeah? So I'm going through this detail because that will help us answer part B. It's asking how much charge. So if we were looking at this so far, so what I just brought up right now, this is the last piece of information that you need to be able to answer this question. How much charge? So, so we know the side. So, about this picture, what do we know so far? Like, what dynamic quantities about this situation do we already know? We know voltage difference. We know electric field. Okay, distance, yeah. So, so let's say those three informations we know, and now we are trying to get to, okay, which of those three things can be related to charge, amount of charge on either plate, so that I don't require any additional information, right? Now, when you're new to problems like this, you might automatically go to this list here, and then maybe even jump to something like this. But then you run into issues when you do that. Like, what issues do you see? So you know the voltage. Yeah, you don't know the energy. And it turns out actually this charge is the wrong charge. That's the test charge. That's not the charges that are in your distribution already. So, I'm just pointing out the kind of traps that you might fall in if you're just going formula hunting. So we know something about voltage and electric field. And let me tell you this. There's a reason that I keep writing down these formulas each time we do electrostatics. There's a reason that I keep writing down these formulas. It's because of how useful they are, provided that you use it correctly. You always whenever you use it, you have to keep the geometry in mind. You cannot misapply them. You have to apply it for the correct geometry. But when you do, these formulas will always tell you this relationship between electric field and the charge and distance. Charge and distance, or here just the charge. So whenever you want to either get electric field from charge or the other way around, charge from electric field, these are the formulas that will connect that if you are using it for the correct geometry. So here, the formula that would connect charge to the electric field, which you know, is this expression here, what we just went through. And this comes from the this is plain electric field formula. So to answer this question of part B, how much charge, this is my starting place. For how much charge, I would start out with, all right, I know the electric field inside the region. I know E naught. And this electric field E naught can be represented in terms of surface charge density sigma. That E naught is equal to sigma over epsilon naught. All right. So what's sigma? Do we have enough information here to calculate sigma? Yeah, we are given we want to know something about charge, and we are given the area for some reason. And this is why area was given. So that you can express sigma as charge per area. I mean, that's the definition of sigma, right? So this is amount of charge per area divided by epsilon naught. So now you can take this expression and solve it for charge. When you do that, this is what you end up with. Q is equal to epsilon naught times area times the strength of electric field And if you want to bring this all the way back to the information that's given in the question, then V naught over D. So epsilon naught area times voltage naught over D. So that's the amount of charge. And here, what I'm kind of trusting, and this is one of the reasons I say units in electrostatics are complicated, I'm kind of trusting that whatever unit this epsilon has makes it all come out correctly so that, area times voltage divided by distance times this constant will come out to be coulombs. I don't usually verify it. I'm just trusting that it'll work out that way. And when you do, it actually does work out that way. Okay? So this is the setup. It's a pretty simple setup, but this simple setup can be used to walk through some of the conceptual topics in electrostatics, and also just applying some of the formulas that were derived that you should know how to use. And I will tell you this setup is important for another reason. So as I confessed the last time, there are many electrostatics demos I have. It's partly because a lot of the things we learn in electrostatics are they're a bit too abstract. So you don't see them in real physical objects that much. But this particular arrangement is an arrangement we call capacitor. That's why I called it parallel plate capacitor. And in fact, I have a picture of what the capacitor looks like. So this is, the picture here is the picture that I drew on the board, more or less. Oops, with terminals flipped around. Now, real capacitors are not made this way. Real capacitors are made with these two plates rolled into each other, so that it's compact in form. And so that as you are rolling it, they don't touch each other. So there's an insulator between them to make sure that they don't touch each other. So there are some pictures of capacitors here. And let me just pass this around. This is a collection of reasonably large capacitance. It's physically pretty big, right? So that's what capacitors look like. It's a circuit component. But today we are just treating it as an electrostatic thing. And this is the idealized representation of a capacitor that we can use to derive some of the properties of it and just talk about capacitance based on what we know about electrostatics. But this is like the first example of an actually practical electrical object that you will see. If you're doing any kind of electrical engineering, then you'll be dealing with the capacitors all the time. So we went through much of the setup already. Just before I mentioned the word capacitor beyond writing it down, we already went through a lot of this already. But let's wrap up this discussion by giving a definition of capacitance. So this is the term I want to define as a new term, but involving the old concepts that you guys already know. So we want to define something called capacitance. So these devices, you don't really have to go through this, but this is how I like to remember things so that I don't forget. It helps me remember what capacitance is. If I have some sense of feeling for what this device is for, like what the purpose of this particular arrangement is. Any guesses? If you were to, build this device, like why would you be building it? What do you think the purpose of building this device would be? Kevin, you're saying something.
Just to control amount of voltage.
Control. Oh, I see. You are thinking about an actual electric circuit. They use this to smooth out the ripples in an inverter. Okay. A little bit too advanced. We are thinking about just the basic electrostatic quantities. I heard some other. Pedro, were you saying something? Maybe Miguel, what were you saying?
I was going to say you can use it as a gate.
Yeah, you guys are all doing advanced circuit stuff. I don't mean that. So, let's say you just saw this device, just the basic fundamental electrostatics. You saw that you could apply voltage to it, and as a result of applying voltage, two different things happened. You established some electric field inside, and you put some charges on the plate. Any guesses which of those two things is more of like what you might want to do as like with this device? Yeah, I guess 50-50 chance. So, here I'm just trying to have you guess intuitively. So one of the effect is that, yes, there's an electric field here. And it depends on the specific device you're building. Sometimes you will be building this device for the actual electric field inside. But when you especially think of this picture, you see that, oh, I'm never going to get to the electric field. Because it's filled with the insulator, I'm never really going to measure anything there. So once you get to this picture of the device, what you are realizing is that what this device is for storing charges on the plate. So the purpose of a capacitor is to store charges. That's at the very basic sense, that's why capacitors exist. So when we talk about capacitance, really what you should have understand as the implication is the capacitance to store charges, like capacity to store charge. So, you see all these mathematical expressions that we went through. So we want to come up with some parameter, capacitance, that we are going to end up calling C. That will be a measure of how well a given device can store charge. So let me tell you this. So one of those quantities that will be involved in defining capacitance C, it's going to be amount of charges, right? We are talking about capacitor to store charge. So I am going to be interested in how much charge is stored there. Yeah? But there's going to be one more quantity involved. Because when you look at the setup of this parallel plate capacitor, so what I'm calling capacitance, I want it to be property of the setup. So when you have a capacitor, the capacitance is the property of this device. I want to say this has capacitance of, 0.05 microfarad. That's the capacitance. I want to say this has a particular capacitance. So it's one of the ways to describe the capacitance will be how much charges are there. But can you imagine taking the same capacitor and right now how much charge would you say is stored on this? 0, right? I'm touching it all over, nothing's happening, it has 0 charge. So what am I changing to change how much charges are actually stored here? What have we changed in this setup to set some amount of charge here? Apply voltage. So amount of voltage that you apply here is going to be the one of the things that determine how much charge. So you have to kind of divide out, okay, should I divide out voltage or multiply by voltage? Divide that out, right? Because the more voltage there is, the more charge you expect. So for capacitance, what you really want is amount of charge per voltage, so that you can use that as property of this device. So that's the definition of capacitance. It's the amount of charge, Q, per amount of V. So voltage that you apply across the capacitor. So this is the definition. And once you have a sense of what the capacitors are for, then this is the intuitive definition. Like there's no other way you would define it. Let's wrap up the discussion of capacitance. We did a lot of the work needed here to actually calculate the capacitance of the parallel plate capacitor. So let's take what we derived all here and then just plug it into this definition of capacitance and see what we get. So according to the definition, this is capacitance. So this would be the capacitance of parallel plate capacitor. So I guess in this setup, we started out by specifying how much voltage there is. So, we specify the voltage here. So let's say, all right, so we are going to divide by voltage. And for the amount of charge, we derived it here. That was question B. So let's just use this charge and see what we get. So when we plug in this expression here, epsilon naught area times V naught over D. You realize, I don't know if I should say surprise or, I mean, we actually should have expected this to happen. If you are saying capacitance is the property of the device, then the voltage should not end up in the final expression. So in this derivation, you see voltage canceling out. So that capacitance is combination of these quantities. Epsilon naught times area over D. Does anything about these three parameters occurring in the capacitance of parallel plate, anything here surprise you? I'm sorry, not surprise. Anything here, what would you, if you had to pick out one category or sort of description of these parameters, what would you say? So, I mean, you know, epsilon naught, that's a physical constant, so let's forget about it. Area A and D, area and distance. What stands out about those two parameters? Chris? You get length quantity. And really what I want you to focus on is that these are geometric parameters. These are completely determined by, well, geometric properties of this capacitor. So this is all rolled up, so it's hard for you to see. But imagine some amount of area, and as you are rolling it up, imagine some amount of distance between them. That's all you need to determine the capacitance. So I want you to have some idea of sense of scale for capacitance. So I want to plug in some numbers. So let me first start by giving you the unit of capacitance. Unit of capacitance is farad. So here in the definition of capacitance, what the left-hand side should be is 1 farad, F-A-R-A-D. I think it's named after Faraday. Who did I thought he did a lot of work with magnetism. Whatever, it's named after a physicist. So 1 farad, so in this equation, you can see how 1 farad relates to other electrostatic quantities. 1 farad is equal to 1 coulomb per volt, right? So if we have a capacitor of 1 farad, then if you put 1 volt across the capacitor, you'd put on a charge of 1 coulomb. Yeah? Does anything about this statement surprise you? No, it doesn't? Okay. Let me pass around my 1 farad capacitor. I got this last year so that I can tell people that I have 1 farad capacitor. So let me pass this around so that you can at least tell people that you have seen a 1 farad capacitor. Please be careful with it. Don't touch the things. It's a very fragile. It can easily break if you apply too much of a voltage like static electricity. I haven't actually used this, so I don't know if they are broken yet. It just says 1 farad on the side. But I want to tell you that 1 farad capacitors, they are unusual. They have been around only in the last 10 years or so. So I want to put in a more realistic numbers here to see what a typical capacitance looks like. So let's just guess. This is a rolled up capacitor. Let's just guess how much area do you think could be rolled up here? Just come up with some reasonable number for area. 10 centimeters, 10 square centimeters? That seems a little bit too small. Let me say 1 square meter. So that would be like 10,000 square centimeters. So I'm imagining a strip of about 1 centimeter strip that can be rolled up around many, many times. So if anything, this is on the high end. Good. And what about for the separation D? Like how small do you think a D should be here? So something small, like smaller than millimeter, right? Let me go small as possible, say 0.1 millimeter. So for separation D, let me use the parameter of 10 to minus 4 meters, 0.1 millimeter. So let's plug in the numbers and see. I don't really want, Let's look up epsilon naught. I should do it. Approximately 9 times 10 to the minus 12. And it's written in some weird units here. I'm just going to say it's a farad per meter. Because that's what the unit has to be. So let me plug in this and see what we get. So these are, I want you to remember, these are sort of the largest number that I can think of, smallest number I can think of. And when you plug it in, this is what you get for the capacitance. With these numbers plugged in, capacitance or parallel plate with these parameters would be, so this is about 10 to minus 11. 10 to minus 11 times the area, 1, divided by 10 to minus 4. So all the units work out to give me farad. It's only 10 to minus 7 farad. And that's actually more typical value of a capacitor. Microfarad is about, you would be able to find the microfarad capacitor all over the place if you have an electronics stockroom. A lot of capacitances actually go a lot lower. Picofarad, 10 to minus 12 farads are also common. So, so that's the sense of scale for the capacitance that I want you to have. And this actually goes with what we said about Coulomb earlier. Do you remember what I said about Coulomb earlier? Like, how large is 1 Coulomb? Very large. It's an unreasonably large amount of charge. So 1 farad, like this 1 farad here, it's an unreasonably large amount of capacitance. So, so this is a special purpose made one that's maybe useful for demos, but most capacitors you will see on computer circuit boards and whatnot, they'll be like around the microfarads. Okay? So that's the capacitance. So I want to use this example of capacitor to talk about energy stored in this setup. What do I mean energy stored? Like, how does this store energy? Like, what would you look at? So if you have a capacitor, like these parallel plates, that's charged up, what would you look at? What would you point to in order to say, this device, once there's some voltage applied to it, that it's storing some energy? Like, what would you point to and say, this is how it's storing energy? You can get this question at different ways. If you have dealt with the capacitors in circuits, there's something that you do use capacitors for to actually answer that.
You use it by determining the amount of area?
Wait, I don't mean determining how much capacitance there should be. I mean, use it actually for a function. So like if you do any kind of photography, then flashlight that releases a lot of energy in a short amount of time, right? A lot of bright light in a short amount of time. The way it works is there's like a capacitor bank that's providing that energy. You first by storing charge on the capacitors and then quickly release it that powers the flash that goes off when you take pictures. But okay, so most of you don't have experience with the circuit, so that's probably not a good way to look at it. So if you're just looking at this setup, this is the typical capacitor setup. Some voltage is set across the 2 plates, which results in charges being stored on the plate. Like, what would you look at to say, this is how I know this thing is storing energy?
Putting energy in there, just putting volts in it, by giving out, depends on how much volts you get back out.
I see. I think what you're trying to, so because you don't put voltage in or out. Yeah. But what you're saying is that when so imagine this is not charged, and when you connect it to the battery, then something comes out of battery. That's what you're putting in, and you're thinking of that as energy, right? Okay. I want to start out with this end state, that this is the snapshot that you have. And in fact, once it's all charged up, once I establish this voltage here, I can actually disconnect the battery. Because this is a static electric situation. The battery doesn't need to be there anymore. Once it's all charged up, then I can get rid of battery and I mean, once I remove the battery, is there any reason for these voltages to change? No, right? I mean, positive charges here, high voltage, negative charges here, low voltage. They can just stay as they are. As long as I don't discharge it, it can just stay as it is. So looking at this setup, I want to look at something to say, I want to point to something and say, this one thing, this is why I can say this setup somehow stored some amount of energy. Yes?
Is it the relationship between the potential energy and the voltage?
Yeah.
Or difference in potential?
Yeah, this relationship here. So, I keep saying this is not the definition, but I keep bringing it up. There's a reason for that. This is almost as good as the definition. This is the fundamental relationship between electric potential and the potential energy. So whenever you relate to something in the electricity to energy, this is the thing you come back to. So here I look at, all right, do I have any charges at some voltage? Then I look at it here and see that I have some charges, plus Q, at some voltage V0. This entire plate is at the voltage V0. So that at least tells me that there must be some energy here. Okay? So now let me get to more concrete question. So what if I asked, all right, so there's some energy here. So I ask you, how much stored potential energy? And let me tell you the wrong answer that I would get most often if the question was just asked. And the wrong answer that a lot of people would say is this one, that stored energy, potential energy, is equal to amount of charge plus Q times the amount of voltage, V0. I keep saying that's the wrong answer. Why is this wrong? Like why, I don't want to go in circles with my leading questions.
Well, it's just, I think it's just the wrong Q equation for the test charge, right?
Okay, what other charges are at this potential other than this plus Q? But the phrase test charge does bring up a good question, yes. Here's one difficulty that you face here. When we talk about this Q test charge here, what we are imagining is that you have some distribution of charge that has already established voltage in the space. And in the space, you are placing a small additional charge Q to see how much energy that additional charge Q has, right? Here, all of that is so kind of jumbled in. These charges minus Q and plus Q are the charges that are establishing the voltage. Now, if I was saying that on top of this, I'm going to place another small charge dq. If I'm placing on another small charge dq here, then I would agree that the energy associated with this small charge, small amount of potential energy that's associated with this, that should be dq times the voltage. Like this is the correct answer. So, here's how I know this is the incorrect answer. How you can know it's an incorrect answer if you're just looking at the formulas that are in the textbook. So, starting from this expression, using the definition of capacitance, you can express this energy in two different forms. Let me write it out so that I have something concrete to look at. So Q times V0, I can turn one or the other into the other quantity using capacitance. Let me turn voltage into charge. So V0 into Q. Then using that relationship, V is equal to Q over C. So we might say V is equal to Q over C. So this should be Q squared over C. You can also turn Q into V using the same expression. Q is equal to C times V. So you might say this is equal to C times V0 squared, right? You might say that's the energy stored on a capacitor, but when you look up the formulas in the textbook, these are not the energies stored in the capacitor. The formulas you would find are 1/2 of these. So the question again, why 1/2? So conceptually, one of the ways to get at that 1/2 is this. Let me give it to you in two different ways. One of the ways is by this consideration. You imagine placing a small amount of charge here. So this is what I want you to imagine. Imagine that this capacitor starts out uncharged. No charge on it anywhere. And you start putting charges on it little by little. Now, the first set of charges you put on here, imagine they are all uncharged. So the very first pair of charges you put on here, positive and negative, did it take any amount of work, any energy to put on these two charges? No, right? Because before these charges, there was no voltage, no electric field, meaning the very first set of charges, they got placed for free. The next set of charges, now it'll start to cost some energy. The next set of positive and negative charges, I'll need to put in some energy. But even then, to place these additional charges, I'm not paying it at the full price of voltage V0. Because until this is fully charged, I don't reach that value of V0. I only reach that value of V0 when it's fully charged. So what you have to remember here is the small amount of energy that you have to pay, that is associated with the small amount of charge you place. And what you have to remember is that voltage is a function of the amount of charge that's already on the plate. So this is a little bit sneaky, unless you were thinking about this explicitly, like it's very easy to forget this. That's why I said, the one without 1/2 is the typical wrong answer I might get, because it's a subtle issue that's really easy to miss. So to get this correct answer, what you would do is start out with the realization that this is the correct starting expression. And if we want to get the full amount of voltage change, full amount of the potential energy change, if we want the full amount of potential energy change, then what you have to realize is that, this is a small amount, and it's going to be a function of the amount of charge. So I cannot simply do final voltage times the final charge. I have to actually do this integral. So I have to actually say, all right, I'm going to have an expression for small amount of potential energy change. I'm going to see how it changes as the charge goes from 0 to the final amount of charge. Write that out here, dq, that's my integration variable, times voltage as a function of charge. I guess I need to know that. Did I erase that all already? Oh, wait, I know voltage is a function of charge. I can solve this for V. So, voltage as a function of charge Q. And using the definition of capacitance, I can say this is equal to Q over C. And C is some capacitance, constant. I can pull that out of the integral. So as charge Q goes from 0 to the final amount of charge. So it's an easy integral, but when you go through it, then we realize where this factor of 1/2 comes from. Let me finish going through that. So set this equal to plug in Q over C. So I have an integral of Q dQ over C, integrate from 0 to Q. What is the antiderivative of this? Yeah, 1/2 Q squared. So it's equal to 1/2, 1 over 2C times Q squared. Evaluate from 0 to capital Q. So you get capital Q squared over 2C. which was one of the formulas here. So that's one way to look at it, that this factor of 1/2 comes from the fact that you actually have to consider the fact that not all the charge Q was placed at this voltage. Some of the charges were placed at 0 voltage. Some of them were placed at this maximum voltage. And when you kind of average it, then you get this factor of 1/2. Okay. Now, conceptually, there's another way to get this factor of 1/2. It comes down to this one example that we didn't do, and I'm really not going to do it in full, but let me just do it as an illustration. Let's say we are trying to calculate the amount of potential energy that's involved in getting this charge separation. Let me say I put it this way. Let's say positive charge here and negative charge here. Sort of kind of like this, except that let's do it with the point charges, so that you can analyze each interaction one at a time. Right? So I think there's actually, is there a more question? There may not be. But if you're doing this question, then this is how you could do. You could count up each pair of interactions. So you can count up amount of energy that's involved in putting together these two pairs at this distance, right? So let me call this PE1 and call this PE2. And are there any other pairs interacting here? There's this, right? Potential energy 3, this pair. Potential energy 4. Any other pairs? There's more, yeah. Potential energy 5 and potential energy 6. All right, any other pairs? Now I'm done, right? So, if I'm dealing with the point charges, this is how I would count up energy. So count all this up and add them all up. That would actually give you the potential energy. And this is one way of doing it. Another way of doing it is this. Conceptually, this is the other way you do count up energy. If you have a charge here that you are considering, then you can calculate the electric potential due to these 3 other charges. Take that electric potential, multiply it by this charge. That would give you the potential energy of this charge. Now, what that does, what the mathematical procedure does, is it counts this pair, and counts this pair. Right? Now, when you do that, you didn't count all the pairs. So you do it for the other charges also. You imagine doing the same thing for this charge. You calculate the electric potential due to these 3 other charges, multiply this charge to that voltage, get some number. So let me call this PA, potential energy B, and do it here, potential energy C, and potential energy D. Now, hearing all that description, do you think those different ways of doing it, that it should be an equivalent description? As in, that, intuitively this is what we think should happen. PE1 plus PE2 plus PE3 plus PE4 plus PE5, one more, plus potential energy 6. When you counted up potential energy by counting up all the pairs of interaction, that should equal potential energy A plus potential energy B plus potential energy C plus potential energy D. Like, should that be true? Whether you count it up by pair, or count it by calculating voltage and then multiply charge, calculating voltage and multiply charge. Now, when you actually go through this calculation, the result you get, so we are not going to actually go through it, but when you do it, this is the result you get. What you get on the right-hand side here, that's going to be twice of what we get on the left-hand side here. Can someone see why that might happening?
You're counting some of the charges twice.
Yeah, we are double counting. So that's why I stopped my description after the first one. Let me continue the description, actually draw lines each time I'm counting the pair. So when I do the calculation for this one, I'm counting this line here, I'm counting this line here, and this line here. You realize that, so these are now counted once, but this is now double counted. So if I did just the A and B, then I would have been in some kind of hopeless place. But something nice happens when I do it for every single charge. So let me do it for D. So I count up this pair here, count up this pair here, and count up this pair here. Right now, some are double counted, some are single counted. Let me soldier on, do it for C. So count up this pair here, this pair here, this pair here. Now do you see that every single pair is double counted? That's why you get this nice relationship that here, it's double the one that you would get from here. So here the correct answer is that this is the correct answer. This answer you get by counting up each pair, making it very sure that you don't double count any one of them. This is the correct answer. Which means there's actually a second way to get the correct answer. You can just take all of this and just divide it by half, or divide by 2, multiply by 1/2. That'll also give you the correct answer. And that's another way of understanding this. Because when you do charge times voltage, this is the continuous limit version of what we did there. So when we do charge times voltage, what we are doing here is we are double counting some of those pairs of interaction. But what we can do is, all right, so we know we are double counting, and we just are going to divide by 2 later. So we're not going to do this a lot, but in the couple examples that you can see, that's the 2 different way of understanding it. One is imagine building up this charge from 0 to some finite value. Do the integral, you get that. Another way to conceptually get it is take this as a given, think of different ways to pair up the charges to calculate it. And when you do it this way, by calculating the voltage at a point and multiplying by charge, when you do it for every one of the charges, realize that you are actually double counting some of the you are double counting all the interactions. So you have to remember to divide by 2 to account for the double counting. Okay. All right. I want to end up this discussion of energy stored on the capacitor with one last way of sort of accounting. So right now, even with these are all based on charges, right? We might have been using voltage or we might not have been, but all these accounting were based on charges. And what we said here is that we have some amount of charge at some voltage, and that's why there's energy. What I want to mention to you is that there's actually a totally different way of counting up energy in an electromagnetic situation. And I want to introduce this to you in the context of capacitor, so that I can recall back to this when we do magnetism after your exam too. So let me just bring this up as just a weird way of counting energy. So this is how I'm going to decide to count energy here. So I'm actually going to ignore all the charges that I see here. Instead, what I'm going to look at as an interesting thing happening regarding electrostatics in this space is not the charge that's here. It's actually the electric field that seems to be set up in this space. And what I'm going to go further and say is, you know what, I don't really care about anything else that's here. I'm just not going to worry about it. What is interesting to me is that there seems to be this region of space with some amount of electric field in that region. So that would be this region here. There's a region of this electric field space with a non-zero electric field, E naught. And outside of this region, electric field is 0. And what I want to say is that the energy density out here is 0, sort of consistent with nothing interesting happening here. And I want to say that in here is where something interesting is happening. There is a non-zero energy density. That's happening in the region with the electric field, that here the energy density is not equal to 0. So it's a kind of weird way to look at it. But when we get to magnetism, you will see the utility of looking at things this way. Because, yeah, so, but for right now, let me just introduce I'll derive the expression and then just leave it there. So the expression I want to derive is the expression for the energy density of electric field. And what's the symbol we use? I think the symbol we use is, don't ask me why, lowercase u. It's kind of based on a common symbol for potential energy is actually capital U, which I don't use because I think people would find this easier. But with this, I have to kind of use the symbol that other people are using. So this lowercase u is the energy density. Let me just derive an expression for that. So what I am going to do is I'm going to just write down an expression for energy that's here. And I guess I have to divide it by volume. So what this energy density will be, it's the total potential energy divided by volume. And I want to express this only in terms of electrical quantities. So Crystal, where can I find the expression for potential energy, electrical potential energy stored in this setup? Because I need to copy it down here to do my rest of the work. I don't think I have erased it yet. Have I? Oh, I may have erased it. Well, in this capacitor, or before I erased all the charges, what used to be capacitor, how much energy was stored in it? I think we wrote down several different expressions. Let's just copy down one of them, and then we'll just use that as a starting point. Sorry, someone was saying something. Oh, so somebody tell me one of the expressions we wrote down for the energy density. I want to say that's the potential energy divided by volume. So somebody tell me an expression for the potential energy stored in the capacitor that we were talking about just now.
Capacity times voltage.
Yeah. 1/2 capacitance. Capacitance times the voltage squared. All right, that's one. So I want to divide it by the amount of volume eventually. So my goal here, this is a complicated expression, right? And I want to reduce this down to a point where the only quantities on this side are electrical quantities. Preferably, I would want nothing but electric field and maybe constant. Because here, my goal is to express how much energy is being stored in the electric field. I don't want any reference to charges. I don't want any other references like that. So, I have this expression, and let me just go through the steps to turn this into something that depends on nothing but electric field and constant. So, I have this voltage here. Let's see. Let me start by getting rid of the capacitance. That's one of the expressions I have not yet erased. So I can use this to get rid of the capacitance of the setup. So let me, and volume, let me write down an expression for volume. How much volume do you think in this space? Like, what's the expression for volume here? Like, what are the geometric parameters you were given before? Yeah, area times distance. Area of the plate times the distance between them. That's how much volume is enclosed between. Okay, so let me write that down. So 1/2 times the capacitance, epsilon naught A over D, that's the capacitance C, times 1 over volume, so that's 1 over area times D, times V naught squared. All right, it's actually beginning to look promising, right? Because you see some of the things cancel out right away. Well, some things don't cancel. Area's canceled, but distance instead of canceling, I get distance times distance. So, all right, that just ends up being something like 1/2 epsilon naught times. Let me group them together. V naught squared divided by d squared. What do you think this is equal to? V naught over d. Crystal? What's V naught over d equal to? I thought you were saying something. So voltage divided by the distance over which you measure the voltage difference. Electric field, right? So looking at this definition here, that's how voltage and electric field are related. So I can say V naught over d is E, electric field. So this expression turns into 1/2 epsilon naught electric field squared. And we'll come back to this later in the semester, but this is the expression for the energy density of stored in a region of electric field. So this is one way to derive it, using this capacitor example. And this is one of the fundamental property of electric field, that whenever you have an electric field, I guess what this means is that must have involved arranging some charges in such a way that those charges were storing this kind of potential energy. But what this expression is telling you is that you don't actually have to look for the charges. So you kind of trust the charges are there, but once you have a region of space with the electric field, then you can skip to this right away without going through the description of what kind of charges do I need to get that electric field. So that's one thing I want to talk about. I should mention a little bit about dielectric because it's an important practical aspect of dealing with the static electricity that we just never spent any amount of time on. So let me do that now. So I think there's a slide in here somewhere that I can use to quickly talk about it. How many here have heard the phrase dielectric? Some people. Okay, if you dealt with the circuits, maybe. So let me explain what the phrase dielectric refers to. So essentially, whenever you hear the word dielectric, think insulator. Think something that has no charge flowing in it. Think any normal material. Think any normal, what is this supposed to be? Element 5. That's not lithium, is it? Boron? I have no idea what it is. Think something that's not a conductor. So insulators, even insulators, are made up of positive and negative charges. When you place it within an electric field produced by these external charges, what you are going to cause it to happen is you are going to cause a separation of these charges. This negative charge is attracting the positive charge, repelling the negative charge. And the positive charge is actually doing similar. It's attracting the negative charge and repelling the positive charge. And the result is that there's a separation of positive and negative charge within an insulating material. So it ends up in a large scale view. This is what it looks like. So when you place it in an electric field going this way, then due to that electric field being imposed on this material, it develops a charge separation, positive charge going in the direction of electric field, negative charge the other way. This is what we call polarization. And every material undergoes it. Even the conductors do undergo polarization. They just do it to such an extreme extent that if this was some kind of conducting sphere, there would be so much positive charge here, so much negative charge here, that inside the conductor, the electric field would be zero. Right? That's the property of conductor. When it's an insulator, so polarizable, I can't say the word. Polarizability. That's one of the properties you can give to a particular material. That's a material property. So conductors are as polarizable as possible as anything. Insulators are still polarizable, but to a lesser extent. Even something like helium atoms actually have a non-zero polarizability. So this is something that happens in a microscopic view. So in the context of capacitors, this is what happens with dielectrics, which once again, by which we mean any kind of insulator. with dielectric, this is what happens in the context of the capacitor. So this is the macroscopic view of what happens when you have a dielectric between the two conducting plates of a capacitor. The dielectric polarizes. Some part becomes negatively charged, some part becomes positively charged. And what it has done, that you can see in this drawing here, is that electric field has been reduced. You have less electric field between the two plates now. Or microscopically, there's still a field line here. It's just that it starts on this positive charge and ends on the negative charge. So for most of this distance, no electric field. So with the reduced electric field, what's the primary effect of that in the context of the capacitor?
It's less interference from other electrical fields it's around or something?
Sorry, interference is a word I do not know.
Okay, like
We did not define the word interference in the context of this class. I want a different word.
if that space had another electric field in it,
Yeah, I don't want a hypothetical. So I want a direct consequence. So we have less electric field in this region of space. So what are the when you have a capacitor, what are the three? Well, name the few properties involved with the capacitor that we care about. So if you have a capacitor, we care about the capacitance. What else do we care about? So the area and distance here, those are the properties that's defining the capacitance, right? So let's say in capacitance, all these are included here. So here, area is not changing, distance is not changing. Tell me some of the other properties that's connected to the capacitor that we care about that may be changing here. Voltage and amount of charge, right? Now in this picture, it was drawn in such a way that the amount of charge remained the same, right? So as you're looking at the capacitance, voltage and the charge, so charge didn't change. That's just the specification for this setup. What can you say about voltage? If my electric field is reduced, what can you say about voltage? Lower voltage. Because once again, this relationship here. Your distance didn't change, but your electric field is smaller. So if you say that this is the voltage difference between these two, VA, for example, then when you look at the voltage difference here, VB, then what you can say based on this picture is that VB is less than VA. The voltage here is less. So connecting it back to the capacitance, when you have a dielectric inside here that reduces the voltage, means that increases the capacitance. So that's, by the way, one of the techniques used in making this 1 farad capacitor. There's a very thin oxide layer which makes the distance very small, and the oxide acts as a dielectric. That helps increase dielectric, which helps increase the capacitance. So that's the one thing about capacitance that, one last thing related to capacitors that I needed to go over. And let me just tell you where all this effect of dielectric enters. So having this dielectric changes all these things, right? It changes the capacitance. So when it's changing the capacitance, the question is, okay, so we had this expression that was derived earlier. What would we change here to make it reflect the fact that there's a dielectric? The thing that we change, or people usually change to make that there's a dielectric there, people usually change this constant. So instead of it being epsilon naught, it'll now be epsilon. So I think I have enough time to just say this last piece of explanation. So when you guys were looking up physical constants, you saw this phrase. When you look up epsilon naught, this is the name that you see in the textbook. This is called permittivity of free space, right? Permittivity, let's say that's some weird old-fashioned term that I have no idea what it's about, but let's say something has to do with the electric, right? What do you think a free space refers to? Free land? No. Yeah, vacuum. So it's referring to epsilon naught, it's a permittivity of a vacuum. So when you change it to epsilon, what you're doing is, well, now the space between them isn't vacuum. There's some material there. So the permittivity of this material will be something other than vacuum. Yeah. So that would be the epsilon. So if you wanted to give it no one actually calls it that way. But if you wanted to give it the name, then it would be permittivity of whatever the material you are dealing with. But it's easier to call it just the dielectric constant. And the way I have written it here, dielectric constant of most materials, it will be bigger than the dielectric constant of vacuum. Because vacuum doesn't polarize, unless to most extent, but most material will, and the result of it polarizing is that it'll make the capacitor greater, capacitance greater. Yeah, so the reason I really want you to talk about this is actually with a view towards when we do magnetism. I used to make a habit of skipping this content thinking I could skip it, but when we get to magnetism, I really need to talk about permeability, and you need to have seen this in the electric context to put that in a proper context.